We have already discussed a few new terms in this course, poles and zeros, in the previous few slides. Let's talk a bit more detail about the last approach of modeling, which is the block diagram. So as I have already mentioned when I introduced block diagram to you, block diagram is nothing more just a pictorial representation of a transfer function, right? It shows the relationship between system and indicates the flow of the signal from the input to the output. There are many types of block diagram. So when I introduce block diagram to you, I have only one block with input and output. That is the simplest block diagram ever. But block diagram can be much more complex than that. So for instance, this is the block diagram, the simplest block diagram that I introduced already to you. I have a system with transfer function of GS with an input R, and the system will respond with output of C. This is one single system. But you might also have a complex system. In such, this complex system consists of subsystems, where each of the system on these subsystems has its own transfer function. So you can arrange this subsystem with some interconnection to represent one big complex system. Another example of this complex system is the one that you show in the right side here, a cascaded block. So in here you have a system where you have two subsystems which are arranged in series. The first subsystem has a transfer function of G1. The second subsystem has a transfer function of G2. A real example of this might be, let's say you have a DC motor. So DC motor has its own transfer function because DC motor is a system. So let's consider the second system, G2 is the transfer function of DC motor. But when you run a DC motor, when you run a motor, what do you need? You need an amplifier, right? You need a power supply to run the motor. So what do? You connect the power supply to the DC motor. And this power supply essentially is also a system. So when you want to run the DC motor, you need to connect this DC motor with a power supply. And then after you connect this power supply to the DC motor, you have a complex system. Now, how to analyze the relationship between the input of the G1 to the output from G2 here. To analyze it, you have to break down these two subsystems and analyze it individually. So if you look at the first subsystem, if you look at this, you have a system with a transfer function of G1, and there is an input R given to G1, and G1 will respond it by giving a output of X. So in this case, X is the output, R is the input, the transfer function is G1. As what we have already discussed, the mathematical representation of this kind of system is output is equal to transfer function times the input. X is equal to G1 times R. Now let's move to the second system. If you look at this, X now is the input to G2 and C is the output from G2. If you look at this again, you can interpret it mathematically that C is equal to G2 times X. If you substitute the first equation to the second equation, you will end up into this equation, right? Okay, if you look at this and you consider C as an output and R as an input, you can see this as a new system with a new transfer function where the transfer function is equal to G1 times G2. So this is the equivalent of the complex system that we discussed before, the cascaded block, the combination of power supply and DC motor. you can consider it as one single complex system with one new transfer function, where the transfer function is equal to G1 times G2. But this is not the most complex block diagram that you might encounter. There might be some other complex block diagram as well, which we will discuss it in the next few slides. Okay, when we are talking about a complex block diagram, more complex than the previous example of a DC motor and power supply of the cascaded block, you might have a complex system that contains a lot of subsystems with their own transfer function, and these subsystems are interconnected to each other. This subsystem can be summed, so you can sum different subsystems by using a summing point. The first picture in this slide illustrates the summing point. So in this case, you might have an output from 3 different subsystems, the output R1, R2, and R3. And then from the summing point, you will have a new output, which is equal to R1 plus R2 minus R3, because you have negative sign for R3 here. But you might also have a case where you have a complex system, and from one of the subsystem in this complex system, the output of the subsystem is branched out to 3 different other subsystems. So you might have also branch point like this. You will see a few more examples on this in application. An example of this kind of complex system is again an air conditioning system. I showed you this picture in our first session when I introduced about the concept of a controller. So perhaps you still remember the story of this. I will brief you again about the story of air conditioning system. So air conditioning system is basically nothing more than a heat pump, but there is a controller and a temperature sensor that monitor the temperature of your room. In such, when you set the desired temperature in your remote controller, you set it to 20 degrees, let's say. Well, for time being, the temperature of your room is 25. The sensor will read the actual temperature of your room, and then the temperature reading will be sent to the controller, right? At the same time, the temperature setting that you set in your remote controller will also be sent to the controller. The controller will compare these two values, 20 and 25. For instance, the actual temperature in your room for time being is 25, so the actual temperature is still higher than the setting temperature. The controller will compare these two values. It will subtract this, so 20 minus 25, you will have minus 5. And the logic of the controller will say if the difference is negative, the controller will ask the heat pump to start. So the heat pump will start, and then your room will become colder. If the difference is positive, which means the temperature of your room is colder than the temperature of the setting temperature in your remote controller, the controller will ask the heat pump to shut down. So expectedly, after some time, the temperature of your room will be more or less equal to the setting temperature that you set in the remote controller. So I have shared this story before in the first session, but then I will represent this system, the air conditioning system, in a block diagram form. So this is a block diagram, a simplified block diagram to represent the air conditioning system. So how to read this? If you look at the first block diagram here, C basically is the temperature of your room temperature. Plant is your heat pump, and RT is the setting temperature that you set in the remote controller. So how does it work? The room temperature will be sensed by the sensor. The sensor reading will be sent to the controller, and at the same time, the setting temperature will also be sent to the controller. The controller will measure the difference between the setting temperature and the actual temperature by through the summing point. If the difference is negative, the controller will ask the heat pump to start. If the difference is positive, saying that the room temperature is colder, the heat pump will be asked by the controller to stop. Okay, so this is the block diagram representation of our air conditioning system. In a simplified version, sometimes the sensor can be considered as an ideal system, can be considered as a static system. So we can omit the transfer function of the sensor. We can consider it as a unity transfer function. We can consider it as a value of 1 here. So you don't have to draw the transfer function in the feedback part of this system. Okay. So this is an illustration of a controlled system of our air conditioning system. All of this subsystem, the controller, the heat pump, the sensors, basically they are a dynamic system. So you can represent this controller, the plant, the heat pump, and the sensor in a transfer function form. So in a block diagram, what you have to put in these 3 blocks of controller, plant, and the sensors are the transfer function of all of those things. The simplified version that I mentioned, when we can consider sensor as a unity function, when you consider the sensor as a static system, when you don't have anything on the feedback part, we call this kind of system as a unity feedback system. These two, the non-unity feedback, the first one, and the unity feedback system, you might encounter it many times in the next few topics, because these are the most common controlled system that you might see in practice. Okay, now let's go back again. We revisit again this closed loop system with this controlled system. So this basically, the controlled system is similar to the controlled system that you saw in the previous slide when we try to represent the air conditioning system. Where in here, of course, HS is the transfer function of the sensor, and GS is a combination of the transfer function of the controller and the transfer function of the heat pump. Both of these system controller and the heat pump are in serial connection, so I can combine it into one single transfer function, right? It's like a 2 system in serial connection, cascaded block. So I can combine the transfer function of the controller and the transfer function of heat pump in one single transfer function block. I call it G here. Now, this controlled system forms a new complex system, a new system. We need to be able to find the relationship between the output of the system, C, and the input of the system, which is R. We need to find this correlation. In such, if you can find this correlation, once you know the input that you give to the system, you can evaluate, you can find the output of the system C. And then if you need, you can inverse Laplace it, and then you can have the response in time domain. But now, before we can do that, of course, we need to be able to find the relationship between R and C. We need to find how this system can be drawn in a simple block diagram by finding the equivalent transfer function of this complex system. So how to do that? We have to analyze part by part in this complex system. The first one, let's take a look on the GS part. If you look at this part, the one that I put in a block, in rectangular block, this, you can see this as a system, as a simple system with a transfer function of G, and to this transfer function we give an input of E, and the system G will respond with giving an output of C. So E is an input to my G, and C is the output from my G. If you have this, what does it mean? Your C, the output, is equal to the transfer function G times E, right? And then now what? I will take a look on this summing point. We discussed about summing point before. So I have summing point. I have two input to this summing point. The first input is R. The second input is minus B. There is a negative sign in here. So what does it mean? This means then the output of the summing point, which is E, E is equal to R minus B. Okay. What next? Let's take a look on the last part, HS. This is again just a simple system, simple block diagram, but I invert it here. So the input is on the right side, the output is on the left side. The input to this system, the input of system H is C coming from here, right? And the output of this system is B. So to this system, to H, B is the output. So BS is equal to HS times CS, right? And then I can substitute this BS to here. At the end, my ES will be equal to R minus H times C, right? Okay, I got these two equations, and then what next? I will just simply substitute this equation, the first equation, to the second equation. Because I have E here, I can substitute the first equation to the second equation by substituting this E, the second equation, to the first equation, and then I will end up into this new equation. You can try it by yourself. At the end, you will get C is equal to G times R minus HC. And then what next? I will just simply do some mathematical manipulation here. I group C with C. So I move this last term to the left side. And then I will get this form, C plus G times H times C is equal to G times R. Again, to our system here, C is the output, R is the input. After I have this expression, I can find the transfer function of this complex system. By what? By taking the ratio between output C and input R. So the ratio between C and R will be as follows. So this is the new transfer function that correlate the output C and input R. This means this transfer function, this block diagram, this complex block diagram can be simplified into a new simple block with this new transfer function. I call this as a closed loop transfer function, the transfer function of closed loop system, a controlled system. In other words, we can say it as a closed loop system. So this complex control system, we can redraw it in a simpler manner with a new transfer function. These two systems are equivalent to each other. So the first block diagram is the control system. After you find the equivalent transfer function, you can represent this control system, this complex block diagram, into simple blocks like that with a new transfer function, whether the new transfer function is equal to G divided by 1 plus GH. We have already analyzed on how to find an equivalent transfer function of a closed loop system. But there are also any other methods if you don't like those kind of calculation. The method is pretty intuitive. I give the recipe of that method in this slide. So you just follow this method step by step. So you analyze it from the output signal. You just follow the arrows in the block diagrams. You repeat it until you arrive again at the output signal. Probably what I say now is not really clear, but let's do it by example here.